Imagine you want a large language model, an AI, to remember things like facts, patterns, or context across a long conversation or huge dataset. But instead of recomputing those patterns every time, what if the AI could look them up instantly, like data from a memory storage? This is the core idea behind Engram, a research initiative and GitHub project by DeepSeek AI that aims to fundamentally change how memory works in large language models. Today we're going to unpack what Engram is, how it works, why it matters, and where it could take the future of AI. By the end of this video, you'll understand why this kind of memory innovation could reshape the whole way we build and scale intelligent systems. At a high level, Engram is a memory module designed to solve a core limitation in current transformer-based large language models. They struggle with efficient knowledge, lookup, and long context recall. Traditional neural models, like GPT or BERT derivatives, rely almost entirely on neural computation to process and generate text. This means they constantly recompute patterns and facts from raw parameters, which is expensive and inefficient. Engram by DeepSeek AI proposes a complementary approach. Introduce a separate memory store that the model can query directly in constant time, O of 1, instead of relearning or recomputing everything from scratch. This is reminiscent of classic Engram memory representations from early natural language processing, but with modern adaptations that allow scalable and efficient integration into large models. The result? Models with Engram can potentially retrieve common knowledge and patterns instantly, freeing up computational capacity for deeper reasoning, much like how a human might look up facts in their memory rather than rededucing them every time. This conditional memory axis fills a gap in transformer architectures, while other innovations like mixture of experts, MOE, improve conditional computation. They don't inherently provide a mechanism for efficient recall of static knowledge. Engram aims to fill that gap by providing a native lookup primitive. The GitHub repository itself contains the official implementation of this idea, offering code, architectural diagrams, and documentation for developers to explore and experiment with. To understand Engram, let's first recall how most modern AI models handle information. Traditional transformer architectures encode everything in weights and attention mechanisms. When presented with a new input, they recompute context from scratch by passing token sequences through multiple layers of self-attention and feed-forward networks. This works well, but it doesn't scale efficiently when dealing with static or recurring patterns, sequences of data that the model ought to remember without recomputing each time. Engram introduces a complementary dimension called conditional memory. It stores static patterns, essentially learned associations or token sequences, in a separate memory structure. Instead of recomputing them, the model performs an O1 lookup, constant time retrieval, for these patterns. This lookup is conditional. It only happens when the model needs it, so common patterns can be fetched quickly without burdening the neural backbone. This idea is innovative because it changes the way transformers balance memory and computation. Instead of relying exclusively on neural computation to recall facts or patterns, Engram treats memory as a complementary piece of the architecture. In effect, it's like giving a model a fast index of knowledge that it can query instantly, leaving the main network free for deeper reasoning and more complex operations. The technical backbone of Engram combines classic Engram embeddings with modern transformer components. At its core, Engram modernizes the concept of Engram embeddings, counting how frequently certain sequences occur, and adapts them for efficient indexing in modern architectures. Engram implements a hashed memory lookup structure so that retrieving patterns doesn't scale with model size or context length. This constant time retrieval is critical for performance gains. In practice, this allows the model to skip recomputing patterns that are already known and stored. Instead of being used for every token, Engram's memory is activated only when a specific pattern or sequence is relevant. This saves computational resources and keeps inference efficient. Once retrieved, Engram memory vectors are fused with the model's dynamic hidden states to influence the final representation. This allows the model to benefit from both fast memory recall and deep reasoning from the neural backbone. It's worth noting that the official GitHub repository provides a demo Python script, engram_demo_v1.py, to illustrate how these memory modules operate alongside a simplified attention/MOE framework. So why is Engram such a big deal? Transformers traditionally struggle with long sequences because every new token must be processed through the same attention mechanisms. Engram's memory lookups can dramatically improve performance on tasks that require long context recall. By memorizing common token patterns and facts, Engram lets the model focus less on rote recall and more on reasoning and complex tasks. Engram mitigates the need for large high-bandwidth memory, HBM, by decoupling static memory storage from the core neural computation. This could make training and inference cheaper and more hardware-friendly. Because Engram scales memory independently of computation, future models could become both larger and more efficient without proportional increases in cost or hardware demand. According to the research behind Engram, models integrating Engram show improved performance on knowledge retrieval benchmarks, reasoning tasks, and complex challenges compared to baseline mixture of experts models with the same parameter and computational budgets. The introduction of static memory helps the transformer backbone focus on global context, improving long context performance significantly. These results suggest that memory-augmented systems like Engram could be a crucial next step in building more capable and efficient AI. No research is without challenges. Integrating memory modules requires careful balancing. Too much memory without context, fusion could misguide the model. Too little may not provide benefit. Efficiently updating static memory during ongoing training or real-world fine-tuning is still an open research area. Hardware and software toolchains must evolve to support variable lookup patterns at scale. But the potential is huge. As AI models continue to grow in size and ambition, innovations like Engram's conditional memory axis may become essential building blocks of future architectures. Engram shows us a future where AI doesn't have to relearn what it already knows, but can instead look it up instantly, freeing up resources for deeper reasoning and complex intelligence. That shift, from computation-heavy recall to memory-augmented reasoning, could reshape how LLMs are built, trained, and deployed. This is not just a code repository on GitHub, it represents a potential milestone in the evolution of artificial intelligence.